Hansang. Okay.
Yeah.
Yes, I think.
I will also share it and then record it. First. Right. Someone already started recording.
Oh yeah, I just started it.
You did it. All right. Okay.
Okay.
Thank you. And great.
Yeah. So this is the Hansang. Yeah, just you said this is the last session before the Easter, right? It's a break. Yeah.
Yeah, it's the break. Yeah, it's the break. Yes. Anyway, before I start that, a bit more additional comment on postdoc 3. So definitely it is a group report. So you just submit only just one report per group or 4. But this time, one thing difference is from previous one is that any additional appendix is not allowed. So strictly 4 pages. You have to put all contents within 4 pages. Over pages, you may get some penalty for over pages. So you fit everything into 4 pages. And I said that the actual performance of radiation performance, we don't really count in final mark unless it is as long as it is some close in some certain range. But anyway, we will open some performance ranking in our revision lecture. So it is kind of a competition. Okay. So let's think about that. And right. And some general feedback about your postdoc 1 and 2 will be given just after Easter. Okay. There's one question. I'm wondering if you will give some examples to test the performance of our group postdoc 3. All examples are given, like the test images and training images. That's all, but no standard or no example to test. So you can just do it by yourself and then provide the code, runnable code, and also your.
So if you want to test, maybe you can separate the training set into different parts, but you can't use the test set. Okay.
No. So but if you want to test for that, probably you can use cross validation.
Yeah.
Yeah. That's one way.
Yeah.
That I use for. Okay. Right. Let's start about the 3D vision stuff. So the 3D vision, the key issue of 3D vision is how to recover some depth information from your photos you have or some videos you have. Because our world is 3D, right? And we perceive all world as 3D, but if you take a photo or take a video of that, they are all projected into 2D plane. And now you have only pixel values on 2D plane. It means that you lose 3D information. Still, we can see some depth or 3D structure from the image, but it is from our knowledge and our brain, but it is not the pixel information itself, right? So the key issue of 3D vision is how to recover that depth information or 3D structure information from 2D images. So it is quite a big issue. Then, before going for that, we may have to check out what is a human visual 3D system. What is 3D human visual system? Surprisingly, human visual system already have all kind of a 3D reconstruction in our brain. So if you see this kind of image, this kind of photo, you can clearly see that this car is closer than this car, right? Nobody will have objection about that, right? This car and this car. This car is closer, right? So how about this car and this car? This car is closer than this, right? And we know that this part of the road is closer than this part of the road. And this tree is much farther. So this tree is closer than this tree. How do you know that? Where's the clue? You can clearly just say, oh, this is closer than that. How do you know that from this image? Do you have any idea? Just type on the chatboard. How do you know that? Don't see any. Size. Wow, that's good clue. Yes, size. Relative size. Yes, this car is much bigger than this, and this car is bigger than that. Anything else? No idea. Yeah, definitely size is the biggest clue, and some other factors you can also consider. For example, this car is occluded by this car, right? This car is hiding some part of this car. From this kind of relationship, you can see that this car is closer than that, right? And in part of the road, you can see that, okay, we assume that this road is straight, right? Reference object, yes, because we know the original size of the car, yes, that's true. That is also size. But they are going towards some point, right? So we can see that this part is closer than that. And we can also see that you can see some colors. This part is it has a bit more like a haze, kind of a bit slightly blurred and then a bit pale in color than this, right? It is called the area perspective. From that, you can also feel some distance. So there are several clues from 2D photos. Even there is 2D photos, we can automatically reconstruct 3D structure from this scene. How do you know that? It is normally called monocular cue. So if you have just one eye or one photo, you can get some depth information. It is from heuristic cues, from your experience and knowledge. Okay. Then there are several factors. First one is motion parallax. It is like a speed of movement is different according to the distance. For example, if you are sitting in the train, and then you can see that, or you are sitting in the car, and then you can see that all road signs are going very, very fast, right? But the houses, which is slightly farther from you, they are moving quite slow. And the mountain behind of that, it doesn't really move at all. But if you move very far, it slightly changes, right? And the moon or sun in the sky, it never moves wherever you go, right? That is kind of motion parallax. If closer, it moves more when you move, right? It changes more. That is motion parallax. And occlusion. Here you can clearly see that the red one is occluding blue one. So you automatically draw this square here on blue here, right? So that is occlusion. You never consider they are in same depth, but this one, blue one, has this kind of shape. You never think like that, right? That is occlusion. Size, very important cues. The same, you know, the size of a house, but this is much bigger because it's closer. Texture gradient here, actually, a similar one shows Xiaohao before. So they have the same size actually, but with this kind of texture gradient, it looks bigger, right? This kind of texture gradient also got good cue for that. There are some more monocular cues, for example, like an area perspective. I showed that you get some kind of haze of texture if it's very far, right? There's something like a foggy. And another one is a very interesting one, the shading. So here you can see that there are two dishes, but one is convex and the other is concave, right? Can you tell which one is convex and which one is concave? You can clearly tell which one is just popped out and then which one is going in, right? But you can see that, you can see that this one is definitely convex. But these two photos are actually same. I just rotated this one 180 degrees, just rotated, and that's this one. The reason that we feel that this one is convex is that in our daily life, normal life, we always assume that the lighting comes from above yourself. So it has some shading, the lower part. So you think that, okay, that is convex. And here, shade is here. So you think that, okay, that is concave, because you assume that the lighting is coming from the top. Right? But if you just rotate it, and then it looks like it's convex, because the shading has been changed. It's got an interesting effect, yeah? It is from your experience, and your brain knows. Another monocular cue is, it's more like a physiological cue. It's kind of focus of your your eye. Actually, your eye lens automatically change is the kind of a thickness to focus to the object. And even you don't think you really feel like that, but actually your brain knows how you are moving your kind of muscle in your eye, and then change the lens and then focus on the object according to its distance. And your brain knows that. And then your brain automatically feels the depth, the point. This is monocular cue. So there are lots of cues. You can get some depth. It's really structured. But is that enough? Why we have two eyes? Well, that kind of monocular cues, you can get that just from one eye. And let's see why we need two eyes to fill in depth. Okay, so everyone just let's test one thing. Just close one eye, left, right, whatever. Just the easier one. Just close one eye, keep close one eye, and then raise up your two index fingers in front of you. Keep your eyes closed, and then try to meet them together. Just like this, and then just close your eye, hold up, and then try to meet them together. How many people were successful in your first trial in meeting them? I don't know. Anyone was successful with that? And then now with two eyes, let's try it again. With two fingers, with two eyes, try to meet them together. Yeah, right. Or with two eyes, let's try it again. It's very easy. Make them meet together, right? So there is some other cue that we feel depth. It is called the binocular cue. The cues we get with two eyes. First one is conversion. So we have two eyes, and then we try to converge two eyes put in to focus that object. Even though we really intentionally do that, it automatically do that. And then our brain knows that what's the convergence angle, and then we can feel the depth. The brain understands the depth of the object. The other one is stereopsis. Normally used for lots of 3D TV or 3D film. You have two glasses, right? So it provides two different images to your left and right eye, and then gives us some kind of feeling of that. Because our eyes they have some distance between two eyes, then left and right eyes are looking at slightly different scene. And our brain automatically merge them and then build 3D structure of them. It's almost an automatic process. You are not intentionally do that, but your brain automatically do that. Okay, so this is our main kind of main principle for 3D film. You provide the left eye, right eye provides slightly different view, and then you feel the depth of scene. So when you wear some glasses, or stereo glasses, they have different parallels. So I forgot the word. Anyway, they have different properties, and then get different two images, and then get 3D structure from that. Okay. Then let's see how we get the images from the 3D scene. We have to understand how we get 3D photo, and then we can reconstruct 3D depth from the scene, from the photo. Right? So this is camera geometry. When we have 3D point, this is a real 3D point, and then this is image plane. We project like a photo with a camera, and this is camera center, and this is image plane. And then this 3D point will be projected some point on 2D plane. Then we want to retrieve this relationship. It is calculated as this is original 3D point, and this is a projected 2D point. There will be some scale factor lambda, according to the resolution of image. Even though the sensor is the same, according to the resolution of a scene, like the size, if it's HD or 4K, the pixel location should be changed, right? So this lambda is a scale factor. So this is a point in the image, XY, and this is 3D point. And this one this equation shows how this 3D point is projected to 2D point by this is extrinsic parameter and this is intrinsic parameter. The extrinsic parameter defines the location and pose of your camera in world coordinate. So definitely photo changes according to the position and then direction of your camera, right? So this one defines that. Where is your camera and then where the camera is looking at, right? So this is rotation metric, 3x3, rotation metric, and this is translation metric, okay? This is 3x1. So this is 4x4 metric. This is called extrinsic parameter, which defines the location and pose of your camera in world coordinate, okay? And then next one is intrinsic parameter. Once it goes through this kind of extrinsic parameter one, then now all images comes to this camera coordinate. So this is center of camera now. There's somewhere there will be world coordinate, right? It can be the corner of your room or the location, whatever. Anyway, from this world coordinate to camera coordinate, this one defines this extrinsic parameter, right? Once this one is done, now it's a projection to your camera coordinate. And the projection of 3D point to your image plane will be calculated by this intrinsic parameter. So intrinsic parameter is the internal parameter of your camera. So if your camera setting is fixed, then you have always same intrinsic parameter. But extrinsic parameter changes according to the position of your camera, right? But intrinsic parameter is internal parameter of your camera. Normally, it is defined by focal length. It depends on your lens and the camera structure. And also, PX, PY is position of principal point in the image. Principal point means the center of image plane, alignment of this the center of image to the camera center. Because normally image center and camera center should be very well aligned. But normally sensor is very, very small, tiny. And then you expect like 4K image from that small sensor. So very subtle change or very subtle error in alignment gives quite big error in image coordinate. So we give this kind of bias. How much is misaligned from actual center axis, image center, the sensor image. Okay? Normally it is very close to center, but sometimes it's slightly misaligned. If we define this intrinsic and extrinsic parameter, then we can project 3D point to image plane. And this one is just the 3x4 matrix because this one is the 3x3 matrix. This one is 4x4 matrix. So projected this 4 point into 3 point. This is just a homogeneous coordinate. So x, y, z to x, y. We need this kind of intermediate matrix. Right. Okay. Right. So finding. So once you take a photo, and then to get some their kind of 3D projection relationship, you have to find this extrinsic parameter and intrinsic parameter. This process is called camera calibration. Okay. By using some special pattern and then taking several photos, you can extract all these parameters. Right? There will be some other intrinsic parameters, for example, radial distribution, or also sometimes we also consider tangential distribution. They are from some lens distortion because normally you use some lens, and lens has some kind of a curvature on their surface, so that they kind of deflect it and then converge into the image center. But sometimes there might be slight error or distortion on the surface, so they make some kind of tangential distortion or radial distortion. But sometimes we also measure this tangential one. They can be also expected from camera calibration. Okay, and the easiest way is to use calibration pattern. It is normally look like this kind of checkerboard pattern. We use checkerboard pattern. And normally, if you have only one camera, single camera, you don't really need extrinsic calibration, because you can just assume that, okay, the world coordinate is the same as camera coordinate. You can just define the world coordinate as, okay, the world coordinate origin will be the same location of a camera. Then probably you don't really need extrinsic calibration. Or if your camera is fixed, then using some several photos of that kind of calibration pattern, you can get some extrinsic and intrinsic calibration parameters of your camera. It is possible for just single fixed camera. It may be okay. But if you have multiple cameras, then you want to get all the 3D poses and then the extrinsic parameters against the world coordinate where you define, and then you need a bit more complicated process to extract their intrinsic parameters and extrinsic parameters. For intrinsic calibration, we use the same, this kind of checkerboard. This one is for calibration for 8 cameras. 8 cameras are looking at the same location, but they are selected in different locations. So we take photos of this checkerboard simultaneously, and then calculate the individual intrinsic parameters for that. And then we use some special method, like extrinsic calibration with some other moving one, or some moving kind of checkerboard. But checkerboard is not normally a good way, because that object should be captured by all multiple cameras. But normally checkerboard is just 2D board. So if one camera is here and the other camera is here, if you place your checkerboard here, only one camera can see the pattern, but the other one cannot see that one. Normally we use some kind of 3D object for extrinsic calibration for multiple cameras. So we use, for example, this one is the one I used before to calibrate the multiple cameras together. So it tracks red ball and green ball, and then track them, and then using some optimization of 8 cameras, and then calculate their location, their extrinsic parameter. Right? So this is one way to do that, but there are multiple ways. For example, actually, this is some demos. So this one is actually this one was a group design project of year 4 students of M engineering group. So I supervised some group design project for year 4 student group, and then they made this kind of calibration tool. They tried to calibrate 2 cameras here and here, but they are depth camera. So they have RGB camera and infrared camera. RGB camera and infrared camera. So there are actually 4 cameras here in slightly different locations, and try to merge them. So in this project, they use these 3 boards, but they are IR reflective boards. So they can be detected by both RGB camera and also IR camera. Here, you can see that they are not really aligned. They just overlaid 2 photos, one from this camera and the other from this camera. But they are not really aligned at all because they are not calibrated at the moment. And this is tracker result. So it's the 3 IR boards with some color. They are detected. And then she just moved the board in different locations, and then automatically it records and track the boards and calculate extrinsic parameters. And then once it's done, and then by extrinsic calibration parameters, they can register 2 cameras into the same world coordinate. Once it's done, then now you can see that now it has some misalignment of images. But once it's done, then they are registered into one coordinate. Maybe it takes a bit more time. Yeah, should be done. Yeah, now you can see that. Now you can just one image. Actually, this one is registration of 2 video streams together into one, with all depth, texture from 4 cameras. So they are now registered like that after extrinsic calibration, because now they are registered into one same world coordinate. This is process of camera calibration. Just the example of that. Okay. Then okay, now we can extract some camera parameters. Then how we can measure actual depth? Once it's projected 2D, then it's 2D point. How can you extract 3D depth from that? First, we can see some narrow baseline stereo first. I already introduced narrow baseline and wide baseline before, right? Just you can just remind that one. Narrow baseline because it's easier. Now you have to understand this epipolar geometry first. So this is a relationship of projection of 3D point. This one is X point to 3D point, right? And this is your camera and your image plane. If you take a photo, then this project will be projected on certain point on the image, right? But now you have only 2D image, and you know this projected X point, right? Then if you know its camera parameters, extrinsic and intrinsic parameters, you can reproject it to 3D page using that kind of position and location information. But problem is that you don't know where it came. It could be this point. Maybe it's original project from here to here, or here to here, here to here. All points on this line will be projected on the same point. So you don't know where it's from. What's the depth, distance to the original point? There's no way to get it. Just only from this one point, right? So with a single camera, it is from this principle, it's impossible to retrieve the depth. But if you have one more camera, if you take a scene from slightly different location and slightly different direction, then you can get it. Because if X is projected here to this camera, there will be another camera, and this one should be projected here, right? And if you know the projection point here and here, they must look quite similar, right? So if you have some matching of this point and this point, then you can triangulate this line. So this is okay. This point should be somewhere on this line, right? But the same point projected here should be somewhere from this line. Then when they meet, okay, that is your original 3D point. It is from. It makes sense, right? Then, okay, we can reconstruct steps from two images, right? Then how can you find this correspondence here and here? This is the key issue. So here are lots of pixels. Here are lots of pixels. You want to find the corresponding point of this one on this image, but it is matching problem. So if it is very distinctive point, probably you can easily find that. But normally it's very hard to find because there will be lots of similar pixels. Then do you have to search all area? Actually, no, because owing to this epipolar geometry, you can reduce some search rate because this point should be somewhere on this line, right? Then this point will be projected here. This point will be projected here in second camera. This point will be here. Actually, all possible points of 3D point will be projected in the second camera on somewhere on this line. They have just one line. So actually, you don't really need to find the corresponding point to this one from here because it's not on the line. There's no chance to be here. There should be somewhere on this line, right? Because it's a projection of this line to this image plane. Actually, you can draw this kind of triangle and two optical centers. If you connect the two optical centers to camera, and then there will be this one is called epipole, and this one is another epipole, and you can make this kind of triangle. And corresponding point of this one will be somewhere on this line. So you can search at this point on this line. Oh, it's here. Then you can triangulate it. Okay, original 3D point should be here. You can find it. This is the principle of epipolar geometry and stereo matching. Okay, but searching it on this line might be a bit more time consuming because this is not. So it says X and Y 2D dimension. So you have to search on this diagonal line. We want to make it a bit more efficient. It is called a rectification. Rectification is just using camera parameters, make two cameras from this contour in, make the image have the same effect so that the two cameras are parallel, like that, looking at the same direction, like that. If you take a photo like this with the absolutely aligned parallel camera, all epipolar lines will be just the horizontal line. So all matching point here will be somewhere on this line. on the same row. So all matching can be just a 1D search, one-dimensional search on the same line in 2 images. All matching point will be aligned in the line using this rectification. So to work that one, so the goal of rectification has actually 2 goals are there. First one is make all epipolar line parallel to find the easy 1D search, and the other one is to correct some distortion of image. So there will be some distortion of image according to your lens, like a radial distortion I mentioned. Then remove that radial distortion effect and then make it kind of a very straight line, straight image. So that is the goal of rectification. Through this kind of rectification, the matching become much easier because you can find only just line by line, and then you can get quite dense matching of that. I have shown this kind of dense depth map before, right? So now we can get different depths. So easiest way to get depth is using stereo camera. In stereo camera, they are already aligned in parallel. So just they can search the matching point on parallel line and then make a triangulation, and then you get this kind of depth. So here depth is quite easy because this B is baseline distance. Baseline distance means the distance between 2 cameras. This is B. And this lambda is some parameter to project some image plane into 3D. So it is kind of they can be also calculated from calibration metric. So you can get them. And there are several ways to that according to your definition of your coordinate. But they normally have some similar form like this. Sometimes maybe you don't get this vector, but only this one. But anyway, once you have some corresponding point, I1 and I2, and then with baseline distance, you can get some depth or some relative depth, which is closer or which is farther, like that. As you can see from this depth map, this is closer, that is farther, right? You can get kind of depth. And the key point is finding corresponding point between 2 images, like finding disparity map, disparity vector. I already introduced one last week, right? So correspondence matching is very important, but in narrow baseline, it's much easier. But in wide baseline, it's harder, especially getting dense map is very, very difficult. This one is in Paris. I hope you recognize this one. Yeah, so point match, you can use some kind of a feature matching between 2 because there are lots of occlusion. For example, this is from absolutely different directions, right? And different time. Now, you can find some correspondence for here and here. That's fine. Maybe they can be matched. For some reasons, like D here, it is not visible in here, right? So you get only just kind of sparse matching, not dense matching, because there are lots of occlusion. It is called occlusion. The reason which is visible in one image but not in the other image. Normally, all stereo pairs they have some occlusion reason. Even some narrow baseline stereo, they have some occlusion reason. But in wide baseline, it's much larger, and it is quite hard to match because this point and this point, brightness are quite different, right? And their structure, the angle is also quite different. So it's kind of the feature matching should be quite a rotation and brightness and scale invariant. So you need much complicated matching algorithm. Normally shift work, but problem is that shift matching gives some sparse matching. So it's much harder. But anyway, and you need much more computation because there are lots of images. Okay. So for example, here you can see some. This is some photo collection. There are some collection of photos on the internet. It's all about Colosseum, but they are collected from the internet, and they capture in different time and different kind of location, different tools, and some occlusion, different people, but they can be all projected. All right. It's a YouTube video, but it's not working. Oh, come on. All right, okay. Yeah. Right, okay, yeah. Now here it is. Video. Yeah, this is Colosseum. You can see the structure of that. Yeah, and here they show some original their pose, camera pose of original photos where they were taken. So here, they jointly estimate the 3D structure and also camera pose, and also intrinsic camera parameters of that. So they just using some kind of optimization method, they extracted all individual camera intrinsic parameters, extrinsic parameters, and also 3D structure of the scene all together here, and then get this 3D Colosseum like this. Okay, like that. This is a, some other example. This one is a much larger area, reconstruction of Venice. And then you can see lots of cameras, photos are here. They use huge number of photos to reconstruct this structure, but they are still quite sparse. As I said, it requires it produces quite a sparse matching from their interest point, right? Anyway, we can get this kind of 3D structure from multiple photos, huge number of photos. It is also possible, but it requires lots of computation. Anyway, this is another hot issue from using some 3D reconstruction from internet collection of photos. Okay. And then, okay, if we have two cameras or multiple cameras, we can get some 3D structure. Is there any way to reconstruct 3D information from just one camera, like monocular vision? Basically, if a camera is moving, then probably you can get some 3D structure because you can assume that individual frame has multiple photos of multiple cameras. So camera is moving, maybe you can get something. But if camera is fixed, then it is very hard to get 3D structure from that. But there's some way, like if you use some more external support. First one is a kind of structured light imaging. You use this kind of pattern, lighting pattern. You project this kind of light pattern on the scene, and then you can get this kind of images, right? They were originally straight line, but here they have some curvatures. They are slightly bent, or they have some discontinuities, right? Then from the assumption that they were originally straight line, just a change of this kind of distortion of multiple lines, you can calculate the 3D structure of that. Okay, it also requires some computation, but it's relatively easier. Then you can get this kind of 3D structure. It's not very dense, but it gives quite good structure. One problem is that anyway, you have to project this kind of beam to the object. So normally in your daily life, it is hard to use because it's a bit quite annoying. If someone project this kind of lace to you, you will be quite annoyed. And it's moving around. The strip is moving around. That's really, really frustrating. But anyway, you can get this kind of 3D structure. It is a bit kind of classical method. So now you can use some non-visible technique. So they still use some kind of rays, but they are non-visible ones. First one might be LiDAR. LiDAR scanner. It's something like a radar, but it's LiDAR. It uses some kind of laser, the single frequency laser. It shoots and then measures the time difference. It is also kind of phase difference when you come back, and then measure the distance. This is extremely accurate because it uses single frequency laser. Actually, this machine is I used this one before, and then the accuracy of that was amazing. The depth error was around 2 millimeter up to 200 meter distance. If you measure some point 200 meter away, the depth error will be still less than 2 millimeter with the maximum accuracy. So using laser, it is instead actually this one is very, very expensive. It was around 30,000 pounds, 40,000 pounds. Yes, much more expensive than normal camera. This is actually the place I used to work before, and then I measured this kind of I captured with LiDAR sensors, And then there are three holes because the eye scanned 3 times because of occlusion. If you scan the scene here, you cannot really see the behind of some object. So I just scan the 3 and then register them all together. And then you can see quite a nice structure of the scene. And then with some color, and then they're structured. They are originally from point cloud, just like this kind of dense point. And it has, at the moment, it has 1.7 million points, but this one is extremely downsampled. In original scan, I got, from only one scan, I get around 50 million points from one scan. It's very, very dense. The problem is that I could not really load onto my machine, on my PC, because of memory problem. So I just downsampled them extremely, like 10 times or something like that. And I also do some other post-processing and made this kind of point cloud. You can see that individual point right here. And you can also generate some mesh from that. But it cannot really detect the windows because Windows does not reflect laser. And some shiny part, maybe it cannot really detect. And there are still lots of occlusion. Anyway, this is one way to measure 3D structure of that. I just wanted to introduce LiDAR sensor. Now some autonomous vehicle have some kind of a part of LiDAR to get some distance to other vehicles. LiDAR is very, very popular in autonomous vehicles now. But it's a slightly different type of LiDAR, much cheaper and faster than this. This one is more like industrial use. So that's why that's too expensive. Other one, something that you can find easily in your life is a kind of Kinect-based one. It is quite a similar one. It also uses some structured light or time of flight, like it measures also distance. Instead of using laser is too expensive, so it uses infrared ray. So infrared camera and the infrared emitter. So it has IR emitter. It projects some kind of pattern there. It's invisible to our eyes, but it has clearly some pattern. And then it does a shot using IR camera. And then pattern, by some template matching, from the pattern, you get some kind of depth. I'm going to show some demo of that. This one is quite simple. So this is kind of pattern, original pattern that it projects. But there's some demo by John. This is actually RGB camera, RGBD camera, Kinect camera, but it has several different modes showing only RGB colors or infrared and show some depth calculated from IR. So here you can see it's just normal RGB. And you cannot see the pattern here because it is not visible to our eye, right? But actually, it is also projecting some IR pattern. If you return to IR camera, now we just change the IR pattern to visible light. Now you can see some distant dots, right? And they are a bit distorted according to the depth and then their pattern of the surface, right? You can see that kind of thing, that kind of pattern I showed you projected on the surface. So IR camera can detect this kind of pattern, and then from the distortion of this pattern and pattern matching, we get some kind of depth. Like now it will show some depth estimation from the IR pattern. Now we get this kind of depth. You can see then the darker, the closer, the brighter, farther. Right? You can see the clear depth. And can you imagine? You can see that there's some kind of gaps here, right? Can you see why? Because it's a depth camera. Why it has this kind of gaps here? Can you guess? Any idea? Why it has these gaps here? That's the object. Very quiet. I don't know. For some time, actually, all students become very quiet during my lecture. Yeah.
So I think my chat box is frozen because I can't see anything. Because it seems someone is saying something. But,
all right. Yeah. No. Yeah. Now someone is saying shadow, brightness. Yeah.
But I can't see anything. So it's.
Oh really? Okay. I can see that then.
Mm-hmm.
Anyway, good guess, but sorry, that's wrong. That's because of also occlusion problem. Actually, even in this sensor, emitter, IR emitter is here, and then IR camera is here. So all IR patterns are emitted from this point, is captured from here. So this part was visible from the emitter. So it is emitted here, patterns were emitted here and here. But when you look at the camera from here, actually this part, there's no pattern because the emitter was emitted from this direction, but you capture from this direction. So this is kind of occlusion, same as a stereo camera. In stereo camera, you use 2 RGB images, but in IR sensor, actually one is emitter, the other one is receiver. That's why it has that kind of gap. Okay. Anyway, but that Kinect sensor is an old version, like more than 20 years old, almost 20 years old, I think, more than 10. Yeah. Now, new version of Kinect is using time of flight rather than IR pattern, because IR pattern has some problem. First one is the resolution. Depth resolution is very low, and then it has lots of noise, right? But now it uses time of flight. It still does the same emitter and receiver, but it shot IR and then measure the phase difference in the receiver. Okay, then it gives a much more accurate depth sense, and then even the density and resolution is much higher. So here's some demo. So this is original RGB camera capture, and this is IR camera capture, and this is the estimated depth from that using time of flight. As you can see, it's much smoother and much more accurate and much denser, right? Still, it has some occlusion around there because the still emitter and receiver have some gaps between them. So, this image. Yeah, you can see it works in real time. Yes, definitely, and it's much more accurate and dense. And this is the 3D projection of that. You can see that. Yeah, you can see this as 3D. Oh, sorry. You can see the 3D object. You can see the big hole because it is projected from this direction, but now it's rendered from different directions. So this part is all occlusion. So if you use single camera, you cannot really avoid this kind of occlusion problem. If you look at from the same direction, that's fine. But if you change your viewing direction, then you can see a big hole behind of that, because the object in front of that is occluded, all part just behind of that. So you have this kind of big hole of that. So you can use multiple Kinect. Actually, this demo is actually I implemented a few years ago using 4 Kinect camera. I put 4 cameras here to surround this kind of area, and then this is a real-time system. One interesting thing is that actually the resolution is not very good, but I used only 1 PC and 4 cameras. 4 cameras are connected into only 1 PC. And even without GPU, the CPU process, it processes all visualization in real time and registration. So it's a very cheap product. But anyway, it's registering all 4 scenes, 4 videos altogether. And then you can also change the viewpoint like that. Right? So this one can be one of the interesting applications of real-time 3D reconstruction using RGBD cameras. So there, I'm gonna just introduce some applications from for 3D computer vision. I imagine you can just guess lots of different applications. So self-driving car is definitely one good because it needs to detect some other cars and also lanes and road conditions, and it should also read all signs of that, right? So Tesla. So self-driving car is definitely you need, but you need more sensors like LiDAR sensor and the camera sensors, multiple cameras, multiple LiDAR, because safety is very, very important here. Any kind of mistake is not really allowed because it makes a really big disaster. It can be also used from architecture, like a 3D building architecture is very common. 3D CAD. Now you don't really draw all line by line by yourself, but they normally do it automatically. Urban planning, I think I have shown this kind of a video, like urban planning, like on the driving car, if they have a camera, they detect the features and track them and then build a 3D structure from them. It is called SLAM, simultaneous localization and mapping. Means it maps 3D space while it moves around from the camera, from the video, it maps 3D point and also localize where the camera is. We can find camera trajectory, their position and location, and then also reconstruct this thing. This is a very interesting area of some for autonomous vehicle or some exploration. Yeah, there are lots of applications. Some virtual tourism, it became quite a hot issue these days because in this pandemic, now you cannot go any trip. So some virtual tourism become a hot issue. Now you can visit museum virtually, or you can visit somewhere like a Google Street View. Now you cannot really go your hometown. Then maybe you can go to Google and then see your hometown with Google Street View. But Google Street View is still 2D, right? It gives 360 viewing angle, but it is still 2D. But there's another one called Google Earth. If you go to Google Earth, you get full 3D structure of that, of your geometry. In most of the time, big town or big cities, maybe you get some 3D structure of that. Okay, or you can also visit some this kind of museums or gallery and enjoy that one as virtual tourism. Or this one might be also interesting, like for your online shopping. You want to find some good fit of your shoes or your clothes. Probably you can. This is quite a clever way. You can try to find some good fit of your sneakers, Nike. I like this guy. Yeah, you can choose your shoes like this. But is there any better way? Yeah, probably using 3D vision, it automatically scans your body in real time. And if you choose some clothes or shoes, it automatically just fit to your body by 3D measurement. It is fully automatic and fully interactive. It should be much fancier than this, yeah? I hope you all agree. But still, you can try this one if you want. So like a chip. It's not even augmented reality, but anyway. Yeah, I love this idea anyway. But 3D vision can provide much better way. Yeah. This one is also used for art and history, like the 3D retrieval of some archaeology, some old object, something in 3D. Or it can be also used for forensic. It can now reconstruct some full 3D of a person from this kind of skull. This is possible. So this one is now normally used in this crime scene, and also analysis of accident. This can be used. Also, it is normally used for surveillance. It's very common. This is GATE system by Professor Mark Nixon in our group. So it is like tracking and analyzing their behavior, like their working style, and then to recognize the person. Or this kind of 3D open pose, it's just a real-time 3D tracker of human behavior, right? And human skeleton. It is also common. And you can also find some motion capture system in film and game production. Traditionally, in this kind of industry, they use this kind of motion capture system. They use some sensors like that. They attach some sensors in their body and they do some action. And then they overlay some 3D character, computer character on them. So this is Gollum, but actually this is a real actor to act this kind of Gollum. And this one is also quite common. And then you can track this one in real time, and then you can replace it with some character. It is very common. But in these days now, this one actually, it is a bit annoying to actors. They cannot really focus and observe and immersive feeling in their action. So now there are many methods going without the marker. Without markers, just from pure video capture, you can get this kind of 3D object. This one is the one project I did like about 10 years ago. We made some short film, and then we had this kind of studio capture of actors, and then also on-set capture, live capture, and then we also get some kind of other background capture separately, and we merged them all into one final movie scene like this. I'm gonna show this one. I'll introduce this project maybe in my special lecture session after Easter. I'm gonna show some more details and also show this short movie clip. So maybe you can get some more information there. Okay. Okay. Let's summarize. So computer vision has lots of practical applications, and they are based on the camera geometry. So camera model gives some mathematical description how 3D scene was projected to 2D image and how we can retrieve the 3D information from 2D image to 3D. The key issue is extrinsic and intrinsic parameter. Extrinsic and intrinsic parameter estimation, which is called camera calibration. If you have multi-views, we can get some depth from that. Or not, maybe we can use some other technique like a laser or IR or some other sensors capture some depth. And now we also use some deep learning to estimate the depth. Deep learning is also very popular for molecular depth estimation these days. I don't deal with that deep learning technique here, but maybe some advanced computer vision module if we can get in the future, that I will introduce that one. But if you are interested, probably you can also find some molecular depth using deep learning. That is also quite interesting. Right, okay. So this is actually the end of my lecture today. Any question? All right, how to prepare final exam? Maybe you don't really need to worry too much. We are gonna have some revision lecture later after Easter. But anyway, just deputy, you have to review all lectures and also coursework. Yes, that's a good way to prepare your final exam. Anyway, it shouldn't be out of scope our lecture. It should be from our lecture, right? And then there's some practice exam beforehand. In revision lecture, we are gonna introduce some previous exam problem, and then we will give some solution of that, a few of that. So you will see that. I think there's also some way to get some previous exam, but you have to remember is that the exam style might be slightly different because the previous one was on site in lecture exam for 2 hours without any book or any references. But this time is online exam, so the style might be slightly different. It means that maybe we may eliminate some exam questions which can be easily looked up on books or internet. So
yeah, so it's open book. Yeah, so it's don't yeah. So the thing is, you need to know, all the content that covered in this in this module. Yeah, but it's open book, so you can get extra resources if you like.
So we will try to measure your understanding, not just memory, but understanding of our lecture. And then probably we may ask how to apply that to some specific task. Probably, yeah.
Yeah. So the understanding the why some transformation, why some kind of algorithm work like that. That's pretty important because so that's basically the questions. Actually, you shouldn't actually worry about too early that thing.
Yeah. The exam time is 2 hours. We are still discussing about that. Like we just were thinking about 4 hours, but 4 hours might be too tiring and too long maybe. But anyway, it's you can just start your time at your own time and then can be 2 hours or 4 hours. We will give some more details after Easter, especially during the revision lecture. But anyway, it shouldn't be too way out of the scope or within the scope of our lectures. So you can just review our lectures again and probably get more.
Yeah.
And maybe before that, you may have to focus more on coursework, especially coursework 3. So try to organize your team and then put the list on the Excel file there, and then just follow the instruction carefully. So after Easter, we will give, and after Easter, first lecture will be about more like feedback, general feedback of coursework 1 and maybe 2, and then give some induction how to program some computer vision tasks about that. So general one and some tips. And then the next one will be a special lecture, some special topic by Xiaohao and myself. And after that, there'll be some, maybe we'll give you some more time to work for your coursework. Okay? Consider offline test? No, this time will be online. This is online.
Yeah.
So you will just take the exam from your home, wherever you are. You can just access and then start your exam and then download it, or just view online and then fill in, then submit online. Yeah, they'll be online.
Yeah.
Okay, right. Then next lecture will be
3 weeks later.
3 weeks later should be 14th of April.
I don't know. So Han-san, I don't know whether the timetable is fixed yet. So, but
right.
In any case, if we got the new timetable fixed, I think maybe we will create the this kind of on your calendar, create the times according to the new timetable. I think it will be the same.
Hopefully, but
hopefully,
yeah. So original plan is that we are not going for face-to-face because anyway, the next lectures will be just the special lectures.
Yeah, so special lectures.
Some feedback for that.
Yeah.
So we are not sure if real kind of face-to-face lecture is required or not.
Yeah.
And we are organizing that, but we assume that we will go for online and this one.
Yeah. So we have about 3. Yeah, I mean 3 lectures plus some kind of revision lectures. So I don't think that's any kind of necessary that we do it face to face. But if you really like that, if you insist that to have some face to face sessions, maybe we can also do some. But yeah.
But if you really want to do that,
and
the majority of you want offline kind of a face-to-face lecture, then you have to let us know as soon as possible because now already.
Yeah.
Yeah.
So the room, lecture room, is very hard to.
Yeah, it is really hard to secure the lecture room.
Yeah. Yeah.
And we also have to discuss with our module leader, John.
Yeah.
We will just discuss about that. And if we want to go for some offline lecture, maybe we can just make a call. Okay, we're going to have to discuss and then put into our team.
Yeah.
Okay.
Yeah.
Yeah.
Good. Yeah. So I think at the moment the main focus for you guys are the 2 courseworks. And so because it will actually be kind of a huge percentage of your final marks. Yeah.
And even for Q&A for coursework, I'm not sure if face-to-face is more efficient or not because it's more like a coding and things.
True.
So I thought like a Q&A session on this team was quite efficient, I think, rather than there are 50 students in the room and then one student asks question, I answer that, all other 40 students are just listening. Ask some other next student ask, and I answer that, and then all the 45 students are not really interested in the question. Just spending 1 or 2 hours for like that. I'm not sure that is a very efficient way or not just for Q&A. But anyway, right, okay, we will discuss with our module leader, and then probably we may leave some poll to ask you if you want or not. Or anyway, we can keep discussing over the Teams channel. Okay, so keep your eyes on Teams channel, checking some other questions and also announcement there.
Yeah.
For your coursework.
Yeah.
Okay.
Yeah. Good.
Great. Thank you very much, and I really enjoyed our lectures. And then see you. Have a good time. Have a good break for Easter, and see you in April.
Yeah. Have a good Easter break here. And see you after
Easter.
that.
And then take care, and then stay safe.
It's good.
See you. Bye bye.
Cheers. Take care.